In this problem, we'll use the multiplication rule with data provided in a contingency table. So we have a summary of 985 pedestrian deaths that were caused by accidents. So let's get our data organized in a contingency table. In our columns, we have information about the pedestrian. Was the pedestrian intoxicated? And so the answers to that are either yes or no. On our rows, we have information about the driver. Was the driver intoxicated? With answers yes or no. So our individual cells have these numbers. Yes, the pedestrian was intoxicated and the driver. There were 59 of these deaths, of these 985 deaths where that was the case, and 79 of the deaths where that was not where the pedestrian was not intoxicated but the driver was. And that row sums to 138. Okay? In the case where the pedestrian was intoxicated but the driver was not, there were 266. And when neither one of them were intoxicated, 581. So this row sums to 847. So our total here, 985. Let's get our column totals here. So this would be 325, and this one would be 660, and this sum is also 985. Of course, those should check. Get the same sum. Okay. So our first question will be part A. If one pedestrian death is randomly selected, if one pedestrian death is randomly selected, find the probability that both the driver and the pedestrian were intoxicated. Both the driver and the pedestrian were intoxicated. Okay, now we're selecting one person or one pedestrian death from our records of pedestrian deaths. Just one selected, and we want to find the probability that that one we select out of 985 has these characteristics. Both the pedestrian and the driver were intoxicated. So we're going to call this particular event, let's just call this event B. So I'll just label it here, B. So the probability of B, where both the pedestrian and the driver were intoxicated, we'll find in our contingency table. And because it's organized so nicely here, this is an easy thing to find. We want to find the intersection of yes, pedestrian was intoxicated, and yes, driver was intoxicated. And we see that it's these 59 people, or deaths, these 59 pedestrian deaths, that represent the situation where both of those conditions are met. So that's going to be the probability, the ratio of 59 people, or I keep saying people, but these are pedestrian deaths. 59 pedestrian deaths out of 985 in this study that was done represent those that both the driver and the pedestrian were intoxicated. So this would resolve to 0.059898, and say we want to round to 5 decimal places. So let's say that's approximately equal to 0.05990. Okay, let's look at part B. If 2 pedestrian deaths are randomly selected, and now you should be thinking right now, okay, you're going to select 2. How are you going to do this? If these are, for example, files in a police department, and you've gone to select out of a group of files, did you pull one out, open it up, record whether or not both were intoxicated, and put it back before you selected the second one? Or did you pull one out and set it aside and then pull another one out, right? So when we do a selection of 2, we need to know, is this with replacement or without replacement? And in this case, we'll say they're randomly selected without replacement. So you pull one file, you set it aside, and then you pull the other. Find the probability that both the driver and the pedestrian were intoxicated. Both the driver and the pedestrian. Were intoxicated. Okay, this is still my event B, both driver and pedestrian intoxicated, but this time I want to know the probability of my first draw. I get a B, both driver and pedestrian intoxicated, and when I reach for another file, I also get that condition, that event B, where both the driver and the pedestrian were intoxicated. Well, because this is without replacement, I would say the probability of B1, this is equal to the probability of B1 times the probability of B2, given that we already have B1. Okay, so how did these numbers come out? Well, we said the probability of just getting 1, which would be like B1, that's the same situation here. On that first selection, there are 59 pedestrian deaths that meet this condition of both driver and pedestrian being intoxicated over 985. But now we've set that aside, so there are only 58 pedestrian deaths left that meet our conditions, and there are only 984 files left in the file drawer, for example. Okay, so this calculation results in 0.0035306, or let's round this to 5 decimal places, 0.00353. Okay, well, perhaps you're thinking, well, wait a minute. Can we treat these dependent events? Would we be able to? I mean, our statement said without replacement. However, if we were working in this situation and said, do I really have to do this? Does the rule apply that would allow me to treat these dependent events as independent events? So let's check that condition. So recall that our sample, we're going to select 2. Our population, there are 985 pedestrian deaths that we have to choose from. So the question we're going to ask is 2 less than or equal to 5% of 985? If we need to answer that question. okay, is 2 less than or equal to 0.05 times 985. That's what, 49.25? So, yes. So, in part C, let's calculate this with replacement. In other words, treat these as independent events. So if two pedestrian deaths are randomly selected, with replacement, now we have independent events, remember, find the probability that both the driver and the pedestrian were intoxicated. Okay, so now our probability of B1 and B2 will just be equal to the probability of B1. On the first selection, we find that they were both intoxicated, times the probability of B2. No conditional probability required. So that would be, on the first draw, we said there are 59 out of 985. But if they're independent events, we say with replacement, so we still have 59 out of 985. Or, of course, we could write that as 59 out of 985 to the second power. And here we get 0.0035878, or to 5 decimal places, 0.00359. And we can see that, maybe not on the same screen here, just barely, that these two are awfully close. And that's due to the fact that we meet these conditions here. So, sampling with replacement and without replacement, in this case, we can choose to treat these as independent events and have the easier calculation. Okay, and another thing I wanted to make sure is clear is how we found this part A. Again, with the contingency table, that made this really nice. It just pops out. We're looking for a selection of one that meets these two conditions. Both the driver and the pedestrian were intoxicated. So we look for the intersection of those two conditions and find the 59 pedestrian deaths that fit that condition. So it's a very nice visual way to work a problem like that when you have a contingency table.